what we are going to discuss today is the size and structure of atomic nucleus. Size and structure of atomic nucleus. Okay, so you all know about the structure of the atom. So we know that there is, if you have an atom, so there is a nucleus inside the atom, and then around that nucleus we have orbitals or shells, whatever you call, different shells, K, L, M, N, and then there on these shells you have electrons are revolving around these shells, depending upon whatever the number of electrons are being filled. So electrons are there. So this is inside this is a nucleus. So these are electrons and negative charge, and so the atomic nucleus of an atom is this tiny space which is positively charged space inside this atom, which contains most of the mass of the atoms. The total most of the mass, almost 90% of the mass of this total atom is contained within this tiny small space, which is of positively charged. And it is responsible, this space is responsible for holding these electrons, which are in these shells, to be revolving inside their respective shells, because this is a positively charged space and these are all negatively charged space. So the attraction balance is there uh, to get these particular electrons in their shells to be revolving around this positively charged space. So the atomic nucleus of an atom is a tiny positively charged space inside an atom, which contains most of the mass of the atom, and to hold the electrons of an atom inside their respective orbits around the nucleus. What is inside the nucleus? Inside the, if you see, if you try to see what is inside this nucleus, so inside this nucleus we have, if this is my nucleus, inside this nucleus we have protons and neutrons. So see, say these are protons, we have protons, and we have neutrons filled everywhere. So these are protons and these are neutrons. So inside this nucleus, so there is a proton and neutron. So proton is a charged particle which is having a charge of plus E, 1 plus E, and neutron is a neutral particle. Neutron is a neutral particle. Neutral particle. It's not having any charge. Conventionally, they all together, proton plus neutron, if we say proton and neutrons all together are called nucleons. They're called nucleons. So the constituents of a nucleus is nucleons, and nucleons are basically the protons and neutrons. Conventionally, you know that a nucleus is symbolized as A. If this is my nucleus, which is chemical symbol, then it has a Z number of protons and A is the atomic number. So this contains So this is how we represent any nucleus, where X is the chemical symbol of element. X is chemical symbol of the element, and Z is the atomic number of the element. This is atomic number, which is basically is equal to the number of protons, or this is also equal to the number of electrons in an atom, and number of proton in the nucleus. Okay, so whatever the number of proton in a system is equal to the number of electron in that particular atom. A is known as the mass number of the nucleus. This is the mass number, which is the basically the number of nucleons. And what is the number of nucleons? This is proton plus neutrons. Okay, so this is how we symbolize an element in which we have number of protons are this, and this is mass number, number of proton and neutron number. For example, this, if you say 1H1, so this means the hydrogen atom. So this hydrogen atom, X is H, Z is number of proton is 1, and because A is 1, so that means there is no neutron. So number of neutron is 0. So A is basically the number of proton and plus number of neutrons. So this is 1. But if you say deuterium, deuterium atom, this is 2H1. So this X is say H, and Z is like this is 1. Number of proton is Z is 1, and what is A is 2. So what is the number of neutrons? So number of neutron is A minus Z. So this is 2 minus 1 is 1. So this atom, for example, the hydrogen, this hydrogen is like, this is the nucleus. This is a hydrogen atom in which we have only one proton. So nucleus contains only one proton. So this is one proton. And then because the proton is 1, so electron has to be 1. So there is only one electron which is residing. This is E plus, E minus, this is E plus. But if we see the deuterium atom, so we have a system in which we have a proton, and we have a neutron. So we have a proton, neutron, and we have a proton inside the nucleus in the atom, and then we have one electron, because the number of proton is 1, so one electron is there. This is what we have. So this is 2H1 and this is 1H1. Okay, so similarly we write 35 chlorine 17. So this has number of proton equal to 17, and number of neutron is, this is A minus Z. So A is like 35, the mass number is 35, minus number of proton, so we have number of neutron equal to 18. Okay, so this is number of neutron. So this is how conventionally we represent the nucleus, which contains the nucleus of an atom, which contains Z number of proton, and this is the atomic number. This, and at mass number A, which this is gives you the number of neutron in the nucleus. So there are some types of mm, you had already studied in class 12th all these. So one, is, you say this is one is isotopes. This some class of nucleus. Isotopes, is already which has same proton proton numbers, but different neutron numbers. For example, we have 35 chlorine 17 and say 37 chlorine 17. So this is isotope of chlorine. Okay, because the proton number is same. The proton number is same. Proton here is 17, proton here is 17. But the neutron number in this case n is 35 minus 17. This will be 18. And for this case 37 minus 17, this will be 20. So neutron number is different. Here is 18, here it is 20, but the proton number is same. So this is such type of nucleus are called the isotopes. Okay, so these two are the isotopes of the chlorine. The second is like isobars. These are having a same mass number, same mass number, but different proton numbers, different proton numbers. For example, we have 14 argon 18 and 14 potassium 19 and say 14 calcium 20. So all these are isobar because the mass number is same, the proton number is different. Because the proton number is different, you can see proton number here is 18, 19 and 20. But the mass number is same, 40, 40 and 40. So such nuclei are known as the isobars. Okay, and the third is isotones. Isotones are having same neutron numbers, but different proton numbers. For example, we have like 31 phosphorus 15 and 32 sulfur 16. So the number of proton here is different. The number of proton is 15 and 16, but the number of neutron here is 31 minus 15 is 16, and here also 32 minus 16 is 16. So number of neutron here is 16, 16 is same, but the number of proton is different. So such nuclei are known as the isotones. There are other parts, isomers and many other things, but these three are standard nuclei differentiation because isotopes, isobar, and isotones. You must remember in your memory. So we know that what is a nucleus? Nucleus is an part of an atom, which is a tiny positively charged space inside an atom, which contains most of the mass of the atom. And they are responsible to hold the electron of an atom inside their respective orbits around the nucleus. And what is the constituents of a nucleus? The constituents of the nucleus are protons and neutrons. Altogether, they are known as the nucleons. And conventionally, we represent a nuclei as A, X, and Z. And you know what is Z, which is A, and what is X. And these are isotopes, isobar, and isobar, the three different class of uh, nucleus or nuclei. How we measure the mass of the nucleus? This is the mass of the nucleus, or the weight of the nucleus is measured in the unit of atomic mass unit. Uh, atomic mass unit. Atomic mass unit, which is, let's just AMU. Okay. So atomic mass is the mass of the neutral atom. Atomic mass is the mass of the neutral atom, not the bare nuclei, not the bare nuclei. So what do I mean by the neutral atom and the bare nuclei? So if I have a nucleus, okay, and then I have a shell around it in which the electrons are there, revolving. So this is an atom. Okay, this is my atom. So atomic mass is the mass of the neutral atom. Why I'm saying the atom as a whole is neutral? Because inside the nucleus we have proton, which is having a positive charge, and these electrons are having a negative charge. And you know the number of protons are equal to the number of electrons. So the total overall, the atom is a neutral. So the atomic mass is the mass of the neutral atom, not the bare nuclei. Bare nuclei means that we don't have these electrons around this nucleus. So bare nuclei means only this part, not the electrons evolving around this. Okay. So the atomic mass, is the mass of the neutral atom. So thus an atomic mass always include the mass of its z electron. Okay. So the total mass is the mass of the nucleus and plus the mass of the say, let me write it like this. Atomic mass is mass of the protons plus mass of the neutrons and plus mass of the electrons, the overall mass of the nucleus. So atomic mass expressed in I told you in atomic mass unit, or represented as U or AMU or U, whatever it is. So how you know already from the 12th class that how you define atomic mass unit. So which is defined as the mass of the 12 6 carbon atom, which is the most abundant atom. This is atomic mass unit uh, is the mass of a single 12 carbon 6 atom. Okay. So this is already defined as 1 AMU as 1 by 12 because it is of single mass of the single carbon atom. So this is 1 by 12 of the mass of an atom of 12 carbon 6, and which is, we calculate, 1.66054 into 10 to the power minus 27 kilogram. So you can calculate it because you know the since 1 mole of mass, 1 mole of carbon atom, you know, is how much? It is of 12 gram. Okay. and this contains 6.022 into 10 to the power 23 atoms, Avogadro number of carbon 12 to a carbon 6. So now from here we can know that mass of one atom, mass of single atom of 12 carbon 6 will be how much? This is 1.9924 into 10 to the power uh, sorry is equal to 12 is 12 divided by 6.022 into 10 to the power 23 atoms of carbon, atoms of 12 carbon 6. So 1 U is now you so this is 1 by 12 into the mass of the single atom of 12 carbon 6, mass of the single atom of 12 carbon 6. So this is 1 by 12 into 12 divided by 6.022 into 10 to the power 23. So this will comes out to be 1.66054 into 10 to the power minus 27 kilogram. So one atomic mass unit is 1.66 into 10 to the power minus 27 kilogram. So what we know is atomic mass unit is the unit in which we measure the atomic mass, and the atomic mass is basically the mass of the proton plus neutron and plus the electron, and this is equal to 1.66054 into 10 to the power 27 kilogram. And now let us move to the size of the nucleus. uh, Size of the nucleus, we know that uh, how to find the size of a nucleus. So we all know about the famous Rutherford alpha scattering experiment. So in which we know that we have a target alpha Rutherford scattering experiment, class 12 you have already learned. We have a target and the alpha scattering particle, alpha is scattered, and then what we found that uh, some of the alpha ray, they are reflected back, some have a very they are reflected back to a certain region. Some of the alpha ray has a very close angle reflection, deflected by very close angle, very close angles, very close angle. Some have been deflected through a very large angles. So this was uh, the experiment, famous Rutherford experiment, on the basis of which uh, it has been concluded that what is the size of the nucleus, what is the structure of the nucleus. So this is the one experiment which had given us the first estimate of the nuclear size. So Rutherford scattering experiment was the first experiment which has given us the first estimate of the nuclear size. The first estimate of the nuclear size, first estimate of the nuclear size was given by the Rutherford experiment. Rutherford alpha scattering experiment. Okay, so in this experiment, you know that an incident alpha particle is deflected by a target nucleus. This is my target nucleus to its closest approach. Like this one is the closest approach in which it is reflected back, or it is reflected back. Some of them had gone past without any deflection. This was also there. So so in this experiment, as we know that incident alpha particle is deflected by target nucleus to its closest approach in a manner consistent with the Coulomb's law. Okay, So this method has provided the nucleus radius to be of the order of around 10 to the power minus 15 meter. So using this method, the size of the nucleus was estimated to be of so radius was estimated to be around 10 to the power minus 14 or minus 15 meters. So this is basically one this is basically one femtometer femtometer, or this is also represented as one Fermi. F and M, one Fermi, known as one Fermi. So since the Rutherford scattering experiment, many other scattering techniques have been developed, and amongst them important is the electron scattering and neutron scattering. So the Rutherford scattering was alpha scattering. So after the Rutherford, many other scattering experiments were planned and have been done, and then in which one is the electron scattering as well as a neutron scattering. So what is the benefit of electron scattering and neutron scattering? So through electron scattering, if we concentrate on electron scattering experiment, we get the information on the distribution of charge. What we get the charge distribution. Charge distribution inside the nucleus, inside the nucleus, and through the neutron scattering experiment, what we get is the nuclear matter distribution. Nuclear matter distribution. So what is the difference between this charge distribution and nuclear matter distribution? Since in the nucleus we have in the nucleus, if we say I have a nucleus in which we have neutrons and we have protons, they are distributed, they are located inside this nucleus. Okay, so we have neutrons and protons inside that. This is proton and these are neutrons. So because in the nucleus we have proton which is a charge. Proton, we have a charge. If we have z number of proton, we have the charge, and this neutron is the neutral particle. It has no charge. So the electron is scattering because the electron is a charged particle. So when electron scattering is there, when we I bombard this nucleus with the electron, then what will happen? This electron is a charged particle and the proton is a charged particle. So this will interact with the proton system inside the nucleus. Therefore, we get the charge distribution. This is nothing to do with the neutron, because the neutron is a neutral particle. So this electron scattering experiment will only give us information how the protons are distributed, and this because the protons are charged particles, so we get a charge distribution, how the charge is distributed inside the nucleus. Therefore, we get the information of the charge distribution. But neutron, if we do the neutron scattering, if we project the neutrons on this particular target, because neutron is a neutral particle, so it will interact differently with the neutrons as well as protons, both the particles. So neutron will interact with the nucleons, protons plus neutron. So it will give the idea about how the neutrons as well as the protons are distributed inside the nucleus, and that total distribution is known as the nuclear matter distribution. So the electron scattering gives us the charge distribution and the neutron scattering gives us the matter distribution, how the proton plus neutron all together are being distributed inside the nucleus. What is found using the electron scattering experiment is that uh, the volume of the nucleus is directly proportional to the number of nucleons it contains. So using these two experiments, either electron experiment or the neutron experiment, the final conclusion was is that the volume of the nucleus. So volume of the nucleus. Okay. Volume of the nucleus, keeping the nucleus, assuming the nucleus to be a spherical system. So volume of the nucleus is found to be directly proportional to the number of nucleons, to the number of nucleons. So if we say V is proportional to number of nucleons is A, proton plus nucleons is proton plus the neutrons. So so number of nucleons means total number of proton and neutron, which is its mass number A. So this is why the volume, nuclear volume, is proportional to mass number A. This means that the density of the nucleons is very nearly the same in the interior of the nucleus. So whatever the part of the nucleus you consider, here, 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 the density at each and every place you will find will be the same, because the volume is directly proportional to how the nucleons are being distributed, the number of nucleon based distributions. So mathematically we can say that V is proportional to A. So because we are supposing the nucleus to be a spherical system, so V will be 4 by 3 pi if R is the radius of the system. If R is its radius, if R is its radius, then 4 pi R cube will be proportional to A. And so this implies that so R is proportional to A to power 1 by 3. And then if you remove the proportionality constant, this is famous expression, this is R equal to R naught A to the power 1 by 3. So this is very famous expression for the radius of the nucleus, which this is mass number of neutron plus protons, and this R naught is experimentally is roughly is of 1.2 Fermi. That means 1.2 into 10 to the power minus 15 meter. So using this expression, we can find the radius of any nucleus. So let me summarize briefly that how we find the size of the nucleus or the radius of the nucleus, because it has been first estimated using the Rutherford experiment, in which we have a target, and the alpha particle is bombarded on the target, and then we have some deflection, large deflection and no deflection, and complete reflection of the alpha particle. And then on the basis of all these analyses of the Rutherford experiment, the radius was estimated to of the 10 to the power minus 14 to 10 to the power minus 15 meter, that is approximately of the order of Fermi. And then after that hmm, uh, using the electron scattering experiment and the neutron scattering experiment, the charge distribution and the matter distribution have been calculated and tried to estimate and the final and the one of the product and the conclusion of these two experiments was that the volume of the nucleus is found out to be directly proportional to the number of nucleons inside the nucleus, which particularly suggests that the density of the nucleons in the interior of the nucleus is very nearly the same everywhere. So and then from here we get this expression R is equal to R naught A to the power 1 by 3, and this R naught is estimated to be 1.2 into 10 to the power minus 15 meter. So using this expression we can find out uh, the radius of many nucleus. For example, let me try to estimate it. First we will try to find for the carbon nucleus. So if we for 12 carbon nucleus, 12 carbon 6, if we try to find the radius, what is the radius of the 12 carbon nucleus? So we know that r equal to r naught a 1 by 3. So if you put the value of r naught is 1.2. So this is 1 point, this is 1.2, and then a is 12 in this case. So this is 12 to the power 1 by 3. And then if you calculate it, this will be in Fermi. So if you calculate it, it will comes out to be 2.7 Fermi. It's very easy. Similarly, if you calculate of this is 1.7 Ag, which is 47. So if you calculate R for this, it will comes out to be 5.7 Fermi. Or more heavier nuclei, if you calculate for 238 uranium 92, and then this R will comes out to be 7.4 Fermi. So one point here is important to be noticed is that from lighter, if you calculate, this is lighter, carbon 12 nucleons. Now it is 107 nucleons are there, like 238. 92 proton is there, and then so much of neutron is there. This is more heavier nucleus. But if we calculate from lighter, go from lighter to heavier nucleus, the radius of the nucleus is like 2.7 Fermi to 7.4 Fermi. So in general, we can say that uh, the radius of the nucleus varies from 2 Fermi to 2 to 8 Fermi. Okay. So considering the nucleus to be a spherical, the radius of the system, all the nuclei, known stable nuclei, are known to be within the 2 Fermi to 8 Fermi. So using very smartly using this r is equal to r naught a to the power of my 3, you can calculate the radius of any nuclear system. And then we can calculate the density, because once we have a radius, we can calculate the density because we have atomic mass, and if we have the radius, we can calculate the volume, and the mass per unit volume, you can calculate the density of uh, any nucleus. So let us try to calculate the density of the carbon 12 system. So you can see the density. If we say density I represent as rho. So this will be atomic mass upon nuclear volume, atomic mass upon the volume, and this is uh, safe represented by m, and then this is 4 by 3 pi r cube. So for 12 carbon, so I'm trying to find it for carbon 6. So the atomic mass of the 12 carbon 6 will be, because the 12 number of nucleon is there, and then it has to multiply it by uh, mm, how much? One atomic mass unit, because this will be 1.66 into 10 to the power minus 27 kilogram per u, and this is 12 u is there, and then we have 4 by 3 into 22 by 7 into like r cube. So r we have already calculated, for which is 2.7 Fermi. So this will be 2.7, and Fermi is 10 to the power minus 15 meter, and then this is the cube of this. So if you calculate this will comes out to be 2.4 into 10 to the power 17 kilogram per meter cube. You see how dense the nuclear system is. So you see 1 meter cube is like 10 to the power 17 kilogram. This is the density of the system. This is very high density, and it is essentially the same for all nuclei. You can calculate yourself for it and you will find it. because the important point is you must remember that it is essentially the same for all nuclei. For all nuclei. That means the nuclear density will of the order of 10 to the power 17 kilogram per meter cube. So if you yourself you try to calculate the nuclear density of 238 uranium 92, and then you will find that the order comes out to be 10 to the power 17 kilogram per meter cube. So if someone asks you what is the order of the nuclear density, and then it has to be 10 to the power 17 kilograms per meter cube. So now we know that this is how we calculate the radius of the nucleus, and this is how we calculate the density of the system of the nuclear system, which is same for all the nuclei. The order is always 10 to the power 17 kilogram per meter cube, and the nuclear radius lies between 2 to 8 Fermi for all the system. Like from lighter system to heavier system, we have gone from 12 nucleon to 238 nucleon. The radius varies from 2 Fermi to 8 Fermi. So for many cases it will approximately go up to like 10 Fermi maximum. Then it will be the surface of the nucleus. Another important point which I would like to discuss about this charge and density. So let me first plot the charge density distribution and matter density distribution. So this is my y-axis, this is my x-axis, and on the y-axis I have the R in Fermi, which is R is the distance from the center. If we have nucleus, spherical nucleus, so R is from distance from the center to the surface. Okay, and then on y-axis we have charge distribution. Charge distribution. Charge distribution means I am plotting the rho p distribution of the proton. So let me this is for oxygen, 16 oxygen. This is for like 118 10, whatever it is. This is for 197 gold, and so on. Similarly for matter distribution, got it. This is R in Fermi. This is matter distribution. Nucleons uh, for Fermi minus Q. Proton plus neutron. So this will be so now you can see that this is my charge distribution and this is my matter distribution. If you want to go from charge distribution to matter distribution, so what I have to do is I have to multiply it by A by Z. The charge distribution, if I multiply it by A by Z, I'll get the distribution of matter inside the nucleus. However, we can expand the experimental findings are through the neutron scattering and through the electron scattering. So important point to be noticed is that if we see the charge distribution, this is the oxygen, the lighter nuclei. The distribution of charge at the center is say is having some value, but as we go on increasing the mass of the nucleus, the distribution at the center, the charge distribution at the center is decreasing from oxygen to 118 to 197. But because this is going to have a smaller radius, and this is going to have bigger radius, this is going to have more bigger radius like 16 oxygen, 10 and oxygen. So the radius is going to be different for different. So that's why the radius system, this system, as this is like plot is from center, and then it goes to the surface. So this is like this from center, the oxygen radius is this much, and then and for this is the radius for so tin, this is the radius for the gold. So for charge distribution, the charge distribution is different for different nuclei, and it's decreasing as we increasing the mass of the nuclei. But inside this, you can see the distribution is almost constant, and then on the surface is slightly, and when you move toward the surface, it slightly decreases. Okay, but uh, if you see to the matter distribution at the center, you can see at the center the matter density is almost same. This is 0.17 Fermi minus cube. 0.17 Fermi minus cube. Because I told you that the matter density is almost same of the order of 10 to the power 7 kilogram per meter cube. So this is not like charge density at the center, which is varying, but the matter density is same here at the center for oxygen as well as for tin as well as for gold. Whatever the size of the radius, size of the nucleus is, the matter density at the center is same. But as we move from center towards the surface, uh, depending upon, this is radius of the oxygen, this is radius of the tin, this is radius of the gold. Okay, so almost inside the matter density is constant. Okay, and at the surface is decreases. This part is same as the charge densities, but this part at the center, the matter density is almost same, but charge density was different. So the density, because is supposed to be almost same anywhere inside the nuclear system, supposing it's of a spherical shape. Okay. Uh, the one important thing I would like to mention here is that which is if we see if we see one structure, if we see one structure of like this, so this can be approximated, such kind of structure can be approximated using the Wood section distribution function. So this is Wood's section distribution function, which is given as this is rho equal to rho naught divided by 1 plus exponential r minus r divided by a. Okay, and where rho naught is 0.17 Fermi minus cube, and this is small r is this is this r, and this r is the radius of the system. And what is a is basically, if you see, this is uh, uh, the 90% the 90% fall of the density. This is 0.9% of rho naught. This is my rho naught, and 10%, this is my 10%, 0.110% of the liquid density. So this region, this slope gives the estimation of a. Okay, so using this, we can fit this distribution of nuclear matter density using the Wood section distribution function. This is an overall brief overview of the size, radius, and charge distribution, and matter distribution of a nucleus, and what are the constituents of the nucleus, and through which experiment we can find out the radius, and they get the idea of the size distribution, charge distribution, that how the protons are being distributed, how the total matter, proton plus nucleons, are being distributed inside the nucleus. In the next lecture, we will try to understand about the stability of a nuclear system through the NZ graph. Thank you.